On the morning of January 15th, 2025, researchers aboard the Spanish vessel Sarmiento de Gamboa documented something that had never been recorded in Antarctic waters before. Methane columns rising 700 meters from the seafloor, venting through fissures in the Earth's crust. Yesterday's understanding of Antarctic stability may never fully recover. The seafloor near the Antarctic peninsula is cracking open, right now, not metaphorically, literally. Fissures in the Earth's crust, some running hundreds of meters long, are venting columns of methane gas straight up through the water column. Columns reaching 700 meters tall, 230 feet wide, rising in silence, in the dark, in water so cold it barely seems real. The Spanish research vessel Sarmiento de Gamboa documented this in early 2025, and the geologists aboard, Ricardo Leon, Roger Urgeles. They weren't alarmed in the theatrical sense, they were precise, methodical. But what they found is the kind of thing that deserves a very long, very careful conversation. Because the number sitting underneath all of this, 24 gigatons of carbon locked in the seafloor of just the surveyed region alone, that number has a context that the news cycle didn't bother giving you. Let me give it to you. 24 gigatons of carbon. That's roughly the equivalent of everything humanity burns, drives, flies, and manufactures for about 2 full years. All of it. Every coal plant, every jet engine, every cement factory, every container ship crossing every ocean. 2 years of that compressed into icy crystalline structures sitting on the Antarctic seafloor, waiting. And now some of it is moving. That's where this story starts. But it is not where it ends. Because what's happening under the Antarctic peninsula connects to a chain of processes. Geological, atmospheric, oceanic, that are all tugging on each other simultaneously, and by the time we get to the end of this video, the thing you thought you were watching, a story about gas bubbles rising through cold water, is going to look very different to you. I promise you that. Stay with me. First, let's understand what we're actually looking at down there, because the mainstream coverage treated this like a curiosity, a scientific footnote, something the research community would quietly sort out over the next decade. But the mechanics of what was found are worth sitting with because they are genuinely strange. The gas being released is methane. It is colourless. It has no smell. It is produced when organic matter, ancient plant material, marine organisms, sediment packed down over millions of years, breaks down without access to oxygen. That process happens constantly in the deep sea floor everywhere on Earth. The difference in Antarctica is the conditions. The water is extraordinarily cold. The pressure down there is immense, and when you combine extreme cold with extreme pressure, something unusual happens to methane. It doesn't just dissolve into the sediment or bubble away, it crystallizes. It locks itself into a lattice of water molecules and becomes a solid, a physical structure. These are called methane hydrates, sometimes called fire ice, because if you take one of these things out of the water and strike a match near it, it burns. A chunk of frozen seafloor sediment that burns. That image alone should tell you how much energy is stored in these formations. Now, these hydrates are not unique to Antarctica. They exist all over the world's ocean floors. The Arctic seafloor is full of them. The continental shelves off the coasts of North America, Asia, and Europe have them too. What made this Antarctic discovery significant, and what made the geologists aboard the Sarmiento de Gamboa stop and measure carefully, is that this was among the first clear, documented evidence of methane hydrate destabilization happening in Antarctic waters. The Arctic has been showing these signs for years. The Antarctic was supposed to be colder, more stable, more insulated from the kinds of temperature fluctuations that trigger hydrate breakdown. The Antarctic was supposed to have more time, and yet, columns of methane, 700 meters tall, rising through faults in the crust. Something shifted the balance down there. The pressure-temperature equilibrium that was keeping those crystalline structures intact, it moved. Enough to crack the hydrates open. Enough for the gas to find the faults in the seafloor crust and push upward. And the expedition didn't just find 1 or 2 of these plumes, they found a pattern, a distribution. And later in 2025, separate surveys in Antarctica's Ross Sea, on the other side of the continent, identified dozens of additional methane seeps in relatively shallow water. Different teams, different equipment, different part of Antarctica entirely. That pattern matters. I'll come back to it. Now I want to walk you through the physics of what happens to that methane once it leaves the seafloor, because this is where the story becomes genuinely complicated, and where most of the coverage got lazy. Methane does not automatically float from the seafloor to the atmosphere and cook the planet. It's not that simple, and anyone who tells you it is either doesn't understand the system or is trying to frighten you without earning it. The ocean is not passive, it is active, it is biological. As those methane columns rise through hundreds of meters of water, two things happen simultaneously. First, some of the methane dissolves directly into the seawater. The ocean absorbs it. This is chemistry. The gas moves from an area of higher concentration into the surrounding water. The colder the water, the more gas it can dissolve. Antarctic water is extraordinarily cold, which means it has a significant capacity to absorb methane before that methane ever reaches the surface. Second, and this is the part that rarely makes the news, there are microbes in the water column that eat methane, literally consume it as a food source. They're called methanotrophs, and in well-studied seep systems, they can oxidize a substantial fraction of the rising methane before it escapes. So the ocean, in effect, has a biological scrubbing system, a living filter built from billions of microscopic organisms doing what they evolved to do. The question, and it is the central question of all the ongoing research, is how much methane is getting through. How much is surviving the water column, evading the microbes, escaping the chemical absorption, and actually reaching the atmosphere? The honest answer right now is, scientists don't fully know. The measurements from these Antarctic sites are still being processed. The models are being updated. What the researchers on that vessel were doing is foundational work, establishing baselines, characterizing the plumes, understanding the geology. The full atmospheric implications are still being worked out. But here is what we do know, and this is the piece I want you to hold on to. Methane is roughly 30 times more effective at trapping heat than carbon dioxide over a 100-year period. 30 times. In the short term, over 20 years, the ratio is even more extreme. This means that even relatively small quantities of methane escaping into the atmosphere carry a disproportionate warming punch compared to the carbon dioxide emissions we talk about constantly. The numbers don't have to be enormous to be significant, and if even a small fraction of that 24 gigaton carbon reservoir begins migrating from hydrate to gas to atmosphere, even slowly, even incrementally, it enters a system that is already under thermal stress. And that's where the feedback loop enters the picture. This is the thing climate scientists call a positive feedback. Not positive in the cheerful sense, but in the systems theory sense, meaning it amplifies itself. Slight warming destabilizes hydrates. Destabilized hydrates release methane. Methane warms the atmosphere further. Further warming destabilizes more hydrates. The loop tightens. The cycle accelerates. How quickly, by how much, on what timeline? Those are the contested variables. But the loop itself is not theoretical. It is physics. It is chemistry. It operates whether or not anyone is paying attention to it. Now let me turn to something that gets even less coverage, the geological stability question. When methane hydrates break down in large quantities, they don't just release gas, they change the physical structure of the sediment. The hydrates, while intact, act almost like a cement. They bind the seafloor sediment together, giving it rigidity, cohesion, structural integrity. When they dissolve, that binding disappears. The sediment becomes looser, more susceptible to movement, and when you are dealing with sediment sitting on a sloped section of the continental shelf, which much of the Antarctic seafloor is, that loosening matters. The possibility being studied, quietly, carefully, by geologists who use words like hypothetical and under certain conditions, is underwater landslides. Submarine landslides, large sections of continental shelf sediment potentially destabilizing and sliding. Now, I want to be precise here, because precision is the difference between useful information and panic. The geologists are not saying this is imminent. They are not saying it is likely in any near-term time frame. What they are saying is that it is a variable that needs to be in the models, and that the historical record shows us it has happened before. There is a place off the coast of Norway called the Storegga Slide. It happened approximately 8,200 years ago. A massive underwater landslide, one of the largest ever documented, released something like 3,500 cubic kilometers of sediment from the Norwegian continental shelf. The tsunami it generated hit the coastlines of what are now Norway, Scotland, and Iceland, with waves that, by some geological estimates, reached 10 meters in height in some areas. The trigger is still debated, but methane hydrate destabilization is considered one of the likely contributing factors. The seafloor chemistry changed, the sediment lost its cohesion, and then it moved. Antarctica's continental shelf is not Norway's continental shelf. The geometry is different, the depth is different, the sediment composition is different. I am not drawing a straight line between Storegga and what the Sarmiento de Gamboa documented. What I am saying is that we have a physical precedent for what large-scale hydrate destabilization can do to submarine geology, and that precedent involves consequences that extend far beyond a chemistry equation about greenhouse gases. Researchers studying the Antarctic shelf are not ignoring this. They are building it into their geological risk assessments. It is a slow-moving concern, but it is a real one. Here's the thread I've been pulling on since the beginning of this video, and now I want to bring it forward. Remember the Ross Sea findings? Dozens of additional methane seeps, different team, different location, same continent. That finding arrived separately from the Sarmiento de Gamboa expedition, but it landed in the same year. And what it tells us, what both findings together tell us, is that these seeps are not isolated anomalies. They are not one unlucky crack in one unlucky stretch of seafloor. They represent a distribution, a widespread pattern across the Antarctic region, and a widespread pattern means the underlying mechanism driving them, whatever that mechanism is, whether it's ocean warming at depth, shifting pressure gradients from changing ice load above, or long-cycle geological processes, is operating at a scale that exceeds any single site. That matters enormously for how we think about the future of Antarctic methane. If this were one location, one fault system, one localized geological feature, you could study it, model it, contain the uncertainty. But when the seeps start showing up across separate basins, across separate geological formations, on opposite sides of the same continent, you are looking at something systemic. You're looking at a continental-scale process beginning to wake up. Antarctica holds the largest ice sheet on Earth. The West Antarctic ice sheet alone, if it were to fully melt over geological time, would raise sea levels by roughly 3 to 4 meters. The East Antarctic ice sheet dwarfs it. These are numbers that represent the reshaping of coastlines, not in our lifetimes, not in our children's lifetimes in the most likely scenarios, but within the frame of human civilization. And those ice sheets are sitting on top of a continental shelf that, as we now know, is laced with methane-bearing faults and hydrate deposits that are beginning to show signs of movement. The weight of the ice sheets, as they change mass, actually affects the pressure on the seafloor beneath them. This is called isostatic adjustment. As ice melts, the land beneath gradually rises, and the pressure distribution across the continental shelf shifts. That shift affects the stability of methane hydrates. Ice loss doesn't just raise sea levels directly, it potentially unlocks the seafloor chemistry underneath. These systems are connected. The ice above and the gas below are in a relationship, and that relationship is being disturbed. I want to say something about the state of the research here, because I think it deserves to be said plainly. The scientists involved in these expeditions are doing exactly what scientists should do. They are measuring, they are publishing, they are flagging uncertainty where uncertainty exists. Ricardo Leon, Roger Orgelis, and their colleagues have been careful and precise in how they've characterized these findings. They have not overstated the immediate threat. They have not claimed certainty they don't have, and that restraint is correct. It is how good science works. The problem is not the science. The problem is the translation layer between the science and the public. The problem is that findings like these get packaged into a 2-paragraph item in a science section, next to an article about a new type of pasta, and then they disappear. What gets lost in that packaging is the cumulative weight of discoveries like this one. Because this expedition's findings do not exist in a vacuum. They sit alongside the Arctic methane seep data, which has been accumulating for over a decade. They sit alongside the ocean temperature measurements showing that Antarctic bottom water, the deep cold layer that keeps these hydrates stable, has been warming at rates that were not predicted even 15 years ago. They sit alongside the accelerating ice mass loss data from the GRACE satellite missions. All of these data streams are pointing in the same direction, not screaming, not creating headlines, just pointing, quietly, consistently, year after year. That's the pattern I keep seeing. Not a single historic event you can point to and say, there, that's the moment. Instead, a slow accumulation of threshold crossings, a gradual unlocking of systems that were stable for thousands of years. A set of feedback mechanisms, each one individually manageable, each one individually uncertain, beginning to interact with each other in ways that were not fully anticipated. The 24 gigatons sitting on the Antarctic seafloor is not a bomb. It is not about to detonate, but it is also not static. It is not simply sitting there, inert, waiting to be catalogued and filed. It is responding to its environment, and its environment is changing. There is one more dimension to this story that I don't want to leave on the table. Underwater infrastructure, subsea cables, pipeline routes, offshore energy platforms. There are thousands of kilometers of fiber optic cables running along the ocean floors of the Southern Ocean. These cables carry internet traffic, financial data, communications traffic between continents. They are not routed arbitrarily. They follow the path of least geological risk, laid along stable sections of the seafloor where surveys suggested the ground would remain predictable. Those surveys were conducted with the assumption that the hydrate fields in certain regions were stable. That assumption is now under review. If submarine landslide risk increases, even modestly, even probabilistically, in regions where these cables run, that is an infrastructure planning problem, not an immediate disruption. But a planning problem that takes decades to address, because rerouting and replacing submarine cables is not a quick project. It is a multi-year, multi-billion-dollar engineering undertaking. The information that would be needed to make those decisions, precise mapping of hydrate distribution, precise modelling of destabilization risk, precise geological survey of the Antarctic continental shelf, is exactly the information that teams like the one aboard the Sarmiento de Gamboa are currently gathering. The research is not abstract. It has direct infrastructure implications, and the pace at which it is being funded, resourced, and acted upon is, let's say, not equal to the urgency of the data coming back. So here is where we stand. The Antarctic seafloor is venting methane through natural faults and fissures. The scale of the hydrate deposits beneath is enormous by any reasonable measure. The ocean is absorbing much of what's released, for now, but the full atmospheric fate of these emissions is not yet quantified. The geological stability implications for submarine sediment are real and are being studied, though no imminent major disruption is being predicted. The distribution of these seeps across the continent suggests a systemic, widespread process rather than an isolated event. And all of this is occurring within a broader context of ice loss, ocean warming, and interlocking feedbacks that compound one another in ways that are still being modelled. This is not a simple story. It does not have a clean conclusion. The honest position is vigilance, sustained, rigorous, well-funded scientific vigilance, at a moment when attention spans are short and the financial commitments to Antarctic research remain fragile. What the Sarmiento de Gamboa found in early 2025 is one piece of a very large puzzle, but it is a piece that changes the shape of what we thought we were assembling. Now I want to ask you something directly, because I think the people watching this channel think carefully about these things, given what we know about how Arctic methane seeps have been documented and largely absorbed into the background noise of climate science for 15 years without triggering the policy response they arguably warranted. Do you think Antarctic methane will get a different reception? Do you think the pattern will change? Leave that in the comments. I mean it. The perspective of people who've been watching this long enough to remember how the Arctic seep story developed, that perspective matters here. If this kind of analysis is useful to you, the kind that doesn't stop at the headline, that walks through the mechanics, that connects the Antarctic seafloor to ocean temperatures to ice loss to submarine infrastructure, then staying with this channel is the way to keep that thread going. Subscribe. Because the follow-up to what the Ross Sea surveys found in late 2025 is going to need its own full treatment, and that story connects back to everything you heard today in ways that are not yet obvious. The ice is old, the gas beneath it is older, and we are only just beginning to understand what disturbing one disturbs in the other.